half-life method. So this is the last method, how to determine the rate law, the order, and the chemical reaction constant. Alright, half-life of reaction, that is T half. I believe this is quite common to you, T half. Time taken for the reactant concentration to fall to half of its initial value. Okay. When Ca is equal to half of Ca0. For example, a reversible reaction A. So I believe this is not reversible, but this is an irreversible, yeah, an irreversible reaction. So having negative Ra equal to KCA alpha, then it is equal to negative dCA over dt. By now you should know this relationship, that is combination between rate law and mole balance. So what you have is, when you combine, you have dCA over dt equal to negative KCA alpha. Okay. Next is, this equation actually comes from the integration of this equation. So we are going to integrate it. So rearrange. So it will be 1 over Ca alpha dCA equal to negative K dt. And you may further simplify this, the integration. As K is a constant, just put it outside the bracket. So the integration is from where to where? Okay, we may start first with Ca naught to Ca. Ca naught to Ca. But later we are going to have this Ca is equal to half of Ca naught later at the end of the steps. And from 0 to T. Okay. So basically for the right hand side, is straightforward. You get negative KT then. Right? For the left hand side, it takes a lot of steps because you have alpha here. So you may present it in different form. Ca. Once you integrate, it will be Ca alpha is supposed to be negative alpha, right? Then minus plus 1. Agree? Once you integrate it, Ca negative alpha plus 1 and divide by the same exponential data. Then this will be Ca naught. This one we already solve it for the right hand side. So you need to solve this equation, and then at the end you are going to replace the T is equivalent to T half. Okay, then your Ca here is equal to half of Ca naught. And at the end, you should get this equation. Alright. Time required for the concentration to fall to 1 over n of the initial value. So basically this is when we derive it, so it is Ca is half of the Ca naught. However, it is actually represented by this general formula. meaning that it's not necessarily half. When n is 2, meaning it's half. Okay, so the 2 will be replaced here. Okay, that's all. The rest will be similar. So if we want to find what is the time required for the concentration to falls to, let's say, 1/10 of the initial concentration, so this n will be 10. Okay, as usual, this equation can be represented by a straight line, a linearized relationship by taking natural log for both sides. Okay, natural log at both sides. Okay, you may try to understand how, because this is all calculus, how by introducing a natural logarithm both sides, you end up with this equation. Okay, so next is, as usual, plot a graph. So the graph will be ln t half as your y, and then ln Cn naught as your x. So 1 minus alpha will be the slope, and this term will be the intercept. So if you look at the figure on your right hand side, so basically this is a plot that will represent the graph when, for example, if the order is 1, so if the order is 1, so if you look at the slope, which is represented by 1 minus order alpha, so 1 minus 1 is equal to 0, so the slope is equal to 0, so that's why it is a straight line. If the order is more than 1, so let's say 3, so 1 minus 3 is negative 2, so you should have a decreasing slope or negative value of slope. And if this order is less than 1, for example 0.5, then you'll have a positive value of slope, for which you'll have increasing trend for log t half versus log C naught. Alright, for this derivation of this equation, don't worry, I'll share the steps. If you have free times, then you can just try. Move on to the last subtopic, that is varying volume batch reactor. What we have earlier is all constant volume. Constant volume. In batch, constant volume. I always put it as, when it's constant volume, for batch is capital V. Volume at the final is equal to volume at the initial. Okay, so you just remain the symbol as capital V for batch reactor. However, we do have batch reactor with variable volume or varying volume. Let's look at the next slide. Okay, this is some explanation, much complex than simple constant volume batch reactor. So if you have variable volume, it means you have complex system. Usually main use would be in microprocessing field, where a capillary tube with a movable bit would represent the reactor. Okay, you may imagine a very small reactor. Okay, it's a tube. Then you have movable bit, so that we can see that the final volume, the volume at time t upon or with respect to the time, reaction time, is no longer equal to the initial volume of the reactor. Yes, we may have this kind of reactor, very small, and let's say a gas reaction is happened. You can see the movable bit, meaning that whether it's increasing or decreasing volume of the reactants in the reactor. This reactor is used for isothermal constant pressure operations for reactions having a single stoichiometry. Okay, this type of reactor, isothermal, having a single stoichiometry, meaning it is not multiple reactions. You only have A plus B, C plus D. You don't have B plus C, and then you may produce E plus F. No. Only single stoichiometry. So for this kind of reactor, variable volume, this is how we put it in the mathematical expression. Volume at the final, or with respect to the reaction time, is not equal to the initial volume. So if not equal, then it is equal to what? It's equal to this equation. Volume at the respective reaction time is equal to initial volume multiplied by 1 plus epsilon A multiplied by the conversion A. Or you may rearrange the formula, then you have in terms of conversion in terms of volume initial and final. Okay, so this equation compulsory to remember. Differentiate the equation. This is just calculus. You differentiate this one. Okay, you'll get this equation. It's very useful when you want to rearrange or having the equation in terms of volume. We already have earlier to replace dCA in terms of dXA. Now dXA in terms of volume. Right? In this case, epsilon is the fractional change in volume of the system between no conversion and complete conversion of reactant A. So that is the definition of epsilon. Fractional change in volume. So volume, when you have a complete conversion, that is x equal to 1, minus no conversion, x equal to 0, divided by no conversion. Okay, volume for the system without any conversion. Okay, if you referring to the previous slide, you have a reactor with a bead. This is initial, and then this is the final. This is initial, final. Okay, let's say the volume here is 1 ml. After the reaction is 1 plus 1. Let's say it is 2 ml. Okay. Complete conversion. Let's say after complete conversion you have 2. And then initially you have no conversion is 1 divided by 1. So the epsilon is equal to 2. So this is an example. So you have reactant A having a reaction produce 4 mole of product R. Alright, this is another a definition for epsilon. It will take the stoichiometric coefficient. Okay, so this is one. So because number of mole is in terms of number of mole is equivalent to Avogadro number, right? So it can be represented as the volume. So for is complete conversion, you have 4 mole of R. So 4, initially you have only 1 mole, so 4 minus 1 divided by 1, so epsilon is equal to 3. Another example, if you have inert, so inert, let's say I, so obviously number of mole is 1, so 4 plus 1 is 5, minus initially you have 1 plus 1, 2, so 3 divided by 2, it is 1.5. Okay. Epsilon accounts for both reaction stoichiometric and the presence of inert. Okay, I'll give you another example, another equation for epsilon, for which you are going to use it a lot in the chapter 3, 4. So epsilon is also, when I say epsilon, it's actually epsilon A. Okay? When there is nothing here, meaning it is referring to the reactant number, the key reactant. Okay, I just put A there. Epsilon A is also can be defined as delta YA naught. So delta is actually the stoichiometric number. It is product minus reactant. Just take this, the first example. Product minus reactant. So delta here is equal to 4 minus 1 equal to 3. Okay, YA naught is the mole fraction of A. So in this case, the mole fraction of A is pure A, right? The reactant is pure A. So YA naught is equal to 1. So if you substitute delta multiplied by YA naught is equal to 3. Similar. Let's look at the inert. Okay, inert. For inert, the delta for this example will be 5 product minus reactant 2. So it's 3. Now look at the YA naught. The mole fraction. Mole fraction here, since it's not given any information, right? So you have 1 mole here and 1 mole here. Because it is not stated. If it is stated, okay, the reactants A is fed to the reactor with excess inert. Then the inert is 10 times to the concentration of A. Then this is 10, this is 1. It's not following the stoichiometric number. So if 10, 1, so YA naught will be 1 over mole fraction. Okay, YA naught is equal to, you can have CA naught for this number of mole, and A naught divided by MP, total number of mole. So in this case, number of mole for reactant A is 1, but total number of mole will be 11. Okay, this is when you are given some information about the feed to the reactor. If not, then we just follow the stoichiometric number. So YA naught is half lah, because you have 1 mole inert, 1 mole reactant. So if you can put NA naught NP, it will be NA naught will be 1. Total number of mole is 2. That's why you have half. So if you substitute in the formula for epsilon A, which is delta YA naught, Your delta just now is 3, and then YA0 is 0.5, then you get 1.5, which is similar to the previous equation, how to define or how to calculate or determine epsilon A. Remember, this is very important. Later you are going to use in chapter 3 and the rest of the chapters, especially when we are dealing with gas phase of reactants, because gas is always variable volume, whether it is in batch, whether it is in the CSR or PFR. Relationship between concentration and conversion for isothermal varying volume, varying density. Obviously, when we have variable volume, it will also affect the density. They have a relationship between that, right? Because density rho is equal to mass over volume. Your volume keep changing, obviously the density will keep changing. So let's look at the relationship between concentration and conversion. Okay, so for this equation, I believe it is common. Concentration is equal to Na, number of mole divided by volume. Na is given by Na0, 1 minus x. Since it's a varying volume, your volume, so this is obviously for batch reactor, is no longer the final, it's no longer to the initial. So it is equivalent to this equation. And then you may have this term to represent by Ca0. Okay, so this is also very important relationship that you need to know, especially when you are dealing with gas phase, varying volume. Alright, so rearrange this one, there's nothing here, just rearrange, and then you may have it in terms of x, meaning you rearrange so that x is equal to is put as a item. So that's all, chapter 2. For that, let's look at the course learning outcome. So this is end of the chapter. I hope by now you should have this knowledge. Okay, ask yourself, are you able to interpret the batch reactor data? Okay, what is concentration, what is number of mole, what is batch reactor, how it operates, what is the important parameters, that will be the concentration and time, or number of mole and time. Okay, examine, number 2, examine rate law using the differential methods of analysis. We have graphical and numerical methods. And then number 3, integral methods, and then method of initial and half-life. Okay, ask yourself, if you're able to solve problems using those knowledge listed here, inshallah, okay, then you may find it is easy to solve problems in the next chapter. Okay, with that, Assalamualaikum.